Hello and welcome to this knowledge-based video. Today, we'll demonstrate how to use filtered radiation field functions in SimCenter StarCCM Plus to evaluate surface contributions to radiation heat transfer on a specific target. This technique allows you to understand exactly how much radiation is coming from different sources inside your domain. First, let's take a look at our example problem setup. Here we have a simplified cabin, which is consisting of an inlet and outlet, a source body, which is generating 20 watts of heat, a top surface on the source body, that's what we're going to be focusing on, and several solid shells for both the aluminum walls and glass surfaces. All solids here are going to be treated as opaque in the simulation. So let's take a look at our physics setup. Here for our physics, we're running steady state with gray thermal radiation, solar loading, and we have a multi-layer solid with two laminates, one for our aluminum and one for our glass. Okay, after running our simulation, we can examine the radiation heat transfer on our top surface. To do this, we can simply create a surface integral report on the boundary radiation heat flux and select, in this case, the top surface within our cabin domain. Running this report gives us 1.6 watts of heat flux going to our top surface. But what if we want to know how much of this 1.6 watts is coming from each surface, the glass, the walls, etc.? This is where the filtered radiation field function becomes valuable. So let's first understand our filtered radiation field function. For more information on this, we can refer to our user guide. This is under physics simulations, radiation, surface radiation exchange workflow, and then visualizing filtered incoming and outgoing radiation. To better understand these field functions, let's examine this simple example. Here we have three solid bodies, a sphere, a cylinder, and a cube. In this case, for our filtered radiation field functions, they have a filter part selection, which determines what part is going to be the input to our field function for evaluating either this incoming or outgoing radiation. So let's say in this example that we pick our cube for both the incoming and outgoing radiation. Here we can see that the filtered incoming radiation, which is the equivalent to a radiation field function, shows the amount of radiation reaching the cylinder and sphere coming from our block. Similarly, if we select the filter outgoing radiation, which is the equivalent to the radiosity field function, this shows the amount of radiation the sphere and cylinder are contributing towards our block. Now let's return to our cabin example and use these field functions. First, let's set our filter for both incoming and outgoing radiation. Here we're going to select the parts filter, and we're going to navigate to our cabin, top surface, and select our top surface within our part. So I'm going to create a scalar scene here. I'm going to select our entire cabin for the parts. And then first we'll take a look at our filtered incoming radiation field function. So when we switch to filtered incoming radiation, we see the radiation on all surfaces that's coming from our top surface, essentially showing how much radiation the top surface is emitting to all other surfaces. Similarly, if we change this to our filtered outgoing radiation, we see the radiation being emitted by other surfaces, which is reaching our top surface. Now to visualize the net radiation heat flux, we're going to create a custom field function. So we have this custom field function called filtered radiation heat flux, and we can see the definition here is simply the filtered outgoing radiation minus the filtered incoming radiation. This represents radiation from other surfaces, which is reaching our top surface, minus the radiation from our top surface reaching other surfaces. So now let's visualize the results with our custom field function. So after we change our field function to filtered radiation heat flux, I'm just going to set the min and max to -5 and +5 watts per meter squared. Now we can clearly see that all the positive values here are areas which are contributing positive heat flux to our top surface. We can see here that's primarily coming from this top glass surface. Negative values, which are in blue, are areas where heat flux is leaving our top surface. You'll also notice that everywhere below our top surface essentially has a value of 0 because simply these surfaces can't see one another. Now let's see how we can quantify these contributions with some reports. So to help quantify these contributions, we're going to create a surface integral report and use our filtered radiation heat flux field function. So when we run this report, we can see we get the same 1.6 watts of heat transfer, but now we get some additional information. We can see that approximately 1.4 watts comes from the top glass surface, about 0.26 watts is coming from our front glass, and we have a net heat loss of -0.06 watts between our top surface and the cabin walls. To further extract some of this value, we can create some additional reports, which can then be used for creating plots or annotations. To do this, we're going to create a new expression report. And here we're going to use the get report value function to extract the specific value. In this example, we'll do the front glass. Here we're going to use our top surface radiation report that we created. And for our filter, we're going to simply use front glass. To better understand the distribution of the heat flux, we can create a histogram plot. For our parts, we're going to select all of the parts of interest, in this case, our front glass, our top glass, and our walls. We'll leave the display mode to stacked. For our bin, we're going to select our filtered radiation heat flux report. To better visualize this, we can additionally set our left axis to a logarithmic scaling. And here we can also set our weighting to the area's magnitude. So this plot now shows the heat flux distribution on our top surface from each source. The top glass not only contributes the most heat transfer, but you can see it also has the highest heat flux values. If we combine all of these elements together, we can create a comprehensive layout. Thank Thank you for watching this knowledge-based video on using filtered radiation field functions in SimCenter StarCSM+. This technique allows you to precisely analyze and quantify radiation contributions from different surfaces to a specific target, providing valuable insight for thermal design and optimization. If you found this video helpful, please check out Siemens Support Center for other knowledge articles and videos.